All right, Chemistry 3111, we're going to continue on with some review for the final exam. And right now we're going to talk about electrophilic additions. And the first question we want to look at is this one right here. Question number 1, what's the major product for the reaction shown? So you can see that we have 1-ethyl cyclohexene, and we're treating that with water and acid. So we have a double bond in the molecule, and we're treating that with, an acid. And so what's going to happen here is that's going to be a hydration, and the addition is going to be a Markovnikov addition, isn't it? Right? If you want to draw out the structure of hydronium, that's fine, but I'll just make a shorthand mechanism. So I'll draw the double bond behaving as a nucleophile, the hydrogen ion, the proton behaves as my electrophile, and then I end up with this carbocation. So let's get some practice drawing our carbocation. So I have 2 carbons here. There we go. There's my carbocation. And then water is going to be able to come in as a nucleophile. And we're going to get a nucleophilic attack there at the carbocation. Maybe I could fix that. There we go, like that. And then, of course, after a proton transfer step, right, you're going to do a proton transfer. So I'll leave that step out. So we got a couple of steps here. And then you're going to end up with a tertiary alcohol. We're not going to get any carbocation rearrangements here. And we end up with this. So 1-ethyl cyclohexanol. And if we look at the possible answers, we see 1-ethyl cyclohexanol right there. Okay, let's move on. Let's take a look at question number 2. It says, predict the major product of the reaction shown. Now, this is kind of an interesting problem here because it's presented a little bit differently than our textbook does, but I went over it with you in class. And so we're taking this 1-methyl cyclohexene and we're treating it with B2H6. So that's diborane. B2H6 is diborane. And then the second step should look very familiar to you, hydrogen peroxide and sodium hydroxide. So these are the conditions for anti-Markovnikov addition of water across a double bond. Now, the B2H6, as I told you in the lecture, this is the same thing as borane THF. Okay, it's just a different, sort of way of writing it down. Maybe it wasn't done in THF or something, but that is nothing more than BH3 THF. Now, the first thing you know, like I said, is that this is going to result in anti-Markovnikov. So the rich will not get richer, right? That means since this carbon is the one that's richest in hydrogens, that means the rich won't get richer. So the hydroxyl, right, the OH, is going to be attached to that carbon. Now, if you look at the possible answers, you see that we have a hydroxyl here, here, and here, but we don't have one here. So immediately we can eliminate C. But that doesn't get us much further, does it? We still have 3 possible choices. Well, I see another big problem here, and that's with this one right here, because here we make a diol. And remember, this is anti-Markovnikov addition of water. So anti-Markovnikov addition of H2O. Okay, so we can cross that one out. Now, if you look at A and B, you want to decide which one is the best answer, right? These both represent an anti-Markovnikov addition. What's the major difference between them? If you look at A, the hydroxyl and the proton that came from the water are on the same side of the molecule. And here, the hydroxyl and the hydrogen are on opposite faces of the molecule. Okay, well, something else that you need to remember about anti-Markovnikov addition of water is that it's a syn. It is a syn addition, SYN addition. And what does that mean? That means that the hydroxyl and the proton are both added to the same face of the molecule. So there's quite a few moving parts here to this one, right? You have to know anti-Markovnikov addition conditions, which are borane THF followed by hydrogen peroxide and sodium hydroxide. And you also have to know that it's a syn addition. So those 2 things are required in order for you to be able to solve this problem. Okay, and also I can't remember. I don't think that our exam ever says B2H6, but just in case you ever see it on another standardized test, or if you're studying, in the future, you're looking over your organic chemistry, it's the same thing as using borane THF. Okay, well, let's move on. Let's try another one. Number 3 is one where you'd probably need to get your scratch paper out. It says, which would be the best method to carry out the following transformation? So we have a little bit of a condensed structure here. We have the two methyl groups on that methine, and then we have a double bond. And what we're doing here is a Markov-Nakhov addition, aren't we? Right? If we look at the 2 carbons in the double bond, the carbon on the right, the CH2, that's the one that's getting richer in hydrogens, isn't it? The other one, the methine, the CH, that one is taking the hydroxyl. So this is clearly, again, this is a Markov-Nakhov addition. Okay. Well, what are the possibilities for doing a Markov-Nakhov addition? Just adding water and acid. That's an idea, right? Now this one here, this is an anti-Markov. These are the conditions for anti-Markov-Nakhov addition of HBr. If we use HBr and peroxide, so that's got nothing to do with what we're trying to do. The next one says borane followed by hydrogen peroxide. That's an anti-Markov-Nakhov addition. But if you look at the last one is the first step is mercuric acetate in water followed by sodium borohydride. That is also an anti-Markov-Nakhov addition. But when do we use this? Okay, this one we can get carbocation rearrangements, whereas these conditions we avoid carbocation rearrangements. And so the question becomes then, am I going to get our carbocation rearrangement if I simply treat this compound, and I'll draw the structure here. Okay, so here we go. This is the compound. If I had an extra carbon. Yeah, I did. 1, 2, 3, 4. There we go. Okay. So if I protonate this compound, am I going to get a carbocation rearrangement? Now, I'm sure that most of you can figure this out, probably faster than I can. But let's just draw a mechanism. So if we have our proton, and I'm just drawing a shorthand mechanism here. After the double bond takes on that proton, let's draw the carbocation that's formed. We end up with this carbocation right here, okay, a secondary carbocation. But what do we know? There's a hydrogen right here, isn't there? And we could get a hydride shift like that, and that is going to give me a more stable tertiary carbocation, and then I can hydrate at that position or add my hydroxyl there, and so I would end up with this molecule as opposed to this molecule. And so that means that A is not your best choice of reagents, is it? Right? A is going to give you a carbocation rearrangement, whereas doing oxymercuration, demercuration, you're going to avoid the carbocation rearrangement. And so again, this is just an oxymercuration, demercuration reaction. So you really need to be on your toes for this kind of stuff and say, okay, well, what's the question really asking me here? Okay, let's move on. Let's try another one. This is question number 4. I think it's also a pretty good question. I might have to go over to the scratch paper to do this one. But it says, it just clearly asks us to do nothing more than predict the product from the reaction shown. So we have an alkene, and we're treating it with HCl, and it just says, what's going to happen? Well, let's go to a blank page here, and let's see if we can figure out what's going to happen. So I'm going to write down the structure. Bear with me here. And I'll write it down the way that they have it. So we have this, and then we have this, and here's our double bond over here. And then we have another ethyl group up here. So what's going to happen when I treat this molecule with HCl? Well, HCl is a strong acid, and it's going to cause a protonation to occur, but we're going to get a Markov-Nakhov addition. So the double bond is going to take on this proton. We're going to lose the chloride like that. Then we're going to end up with a carbocation. Let's draw that carbocation. So it's going to look something like this. There we go. There's our carbocation. And the question becomes, can this carbocation undergo a rearrangement? And the answer is yeah. If we draw this hydrogen explicitly here, you can see how if we have a hydride shift, right? This is a hydride shift, okay? Then we're going to end up with a more stable carbocation, aren't we? We're going to go from a secondary carbocation to a tertiary carbocation. We have this triethyl carbocation. There we go. And now the chloride can come in as our nucleophile. And we're going to get nucleophilic attack like that. And then we're going to end up with our final product. I'll just draw the bond line structure of the final product. So we have an ethyl group, another ethyl group, and another ethyl group, and we have our chlorine like that. So there's our final product. Good. So what did we learn here? You know, you have to be able to recognize when it's a Markovnikov addition, and you got to be able to recognize when a hydride shift is going to occur. And if we go back here, you'll see that the answer is A. A is the answer. A is the answer right there. Okay, next question I had chosen was question number 7. We'll move on to there. Nothing more than just asking us, you know, what set of reagents would you use to carry out the following conversion? Well, if we examine the carbons of the double bond, this one has 1 hydrogen attached to it, and this one has 2. And so the rich are not getting richer here, are they? This is an anti-Markovnikov addition of water across the double bond, right? Because we're adding a hydroxyl and we're also adding a proton over here in addition to the one that was already there, right? And the 2 that were already here. Okay, and so what are the conditions for anti-Markovnikov addition of water? Is it water and peroxides? No. Is it just treatment of the compound in water with aqueous acid? No. What about borane, okay, or diborane followed by hydrogen peroxide and sodium hydroxide, right? That's a 2-step process, and that is the correct answer. We went over that earlier today. And then the next one is oxymercuration, demercuration. No, because we know that that gives you Markovnikov addition, and it avoids, the only reason you would use that is to avoid carbocation rearrangement. All right, let's move on to question 8. I think question 8 is another one that we might need some scratch paper to solve. It says the addition of bromine to E3-hexene, that's this molecule right here, will give, and then we have a whole bunch of, it could be a meso compound, a pair of enantiomers, 2 meso compounds, 4 stereoisomers. Well, this is one of those questions where you need to know a little bit about mechanisms in order to figure out what the final product is. But the good news is that our book asks this question or something very close to it several times. I know this kind of question comes up where it gives you a trans or a cis compound and then gets you to do dihydroxylation, syn dihydroxylation or anti-dihydroxylation or bromine, whatever, right? So he always gets you to kind of decipher these types of problems. Well, let's go back to the scratch paper here and see if we can't muscle our way through this one. Let's see here. So I'll start by redrawing the compound, the trans or the E3-hexene, so which is also a trans 3-hexene. So here we go, like that. Now you need to know a little bit about mechanisms here, right? And this is a bromination mechanism, right? If we're treating this with Br2, right, bromine, and I asked you to learn this mechanism way back in Organic Chemistry 1, right? We end up forming what? Okay, we end up doing something like this, right? And in the first step, we form our bromonium ion. Okay, so let's draw what the bromonium ion would look like. But I'm drawing it so it looks like the bromonium is going to be attached to the bottom face like that. So let's draw what that would look like. Okay, so we're going to have a carbon. We're going to have single bond now. And in the back, right, we're going to have this ethyl group. Oops, methyl. This ethyl group. In the back here, we're going to have this proton, and then kind of coming out in front, we're going to have the ethyl group here. There we go. And then coming out in front here, we're going to have this proton, and then underneath, you're going to have the bromonium ion. All right. Okay. So we have our bromonium ion like that. And this is the bromonium ion. And what did we do? We lost bromide in the process. And now the bromide is going to come in as a nucleophile. Now, since there's a plane of symmetry through this intermediate, it doesn't matter which carbon you draw attacking. But let's just see what's going to happen. Let's attack this carbon right here. Okay, if it attacks that one, this ring is pretty strained. And so this is going to pop open like this. Now let's draw what the final product would look like. Well, when that bromide does the attack here, right? The bromide is going to be coming out on the top, okay? And that's going to push the proton and the ethyl group down, okay? So this is an inversion, but it's not going to be like we flip the wedge and the dash, right? They're just going from the top face of the molecule to the bottom. Let me show you what I mean. Okay, so we get that nucleophilic attack. Let me fix my red curved arrow here. Then this carbon, okay, so let's draw the two carbons. The hydrogen is still in the back, but now it's pointing down, right? You see here it was up on the top face, and this guy was supposed to be up as well. But now the ethyl group is going to be going down. I'm just going to write ET for ethyl to keep it short, okay? We're going to have the bromine up here, okay? Now this bromine is going to be pointing down. Let's draw that. We have our bromine pointing down like this. This ethyl group didn't change, and this hydrogen didn't change. So, what type of compound is this? Okay, are we dealing with, a chiral compound? Are we, what are we going to get? Well, if you rotate this bond, okay, if you rotate that bond so that the bromines are on the same side and in the same plane, what would you get then? It's going to be the same thing as this. We draw this, okay? So we still have our hydrogen going in the back like this. We still have this ethyl group coming out in front like this. But this ethyl group that was in the back is now going to be in the front when I rotate this, right? Because all I'm doing is I'm rotating that bond by 180 degrees. So instead of the ethyl group being in the back, it's going to be out in front like this, and the proton is going to be in the back. And so you can see that this is, in fact, a meso compound. And so if we go back to the possible answers to this one, where was it? We're going to end up with one meso compound in this case. So just one compound is going to be formed. All right, so what do you have to know here? You have to know the mechanism of bromination. All right, you have to be able to recognize what a bromonium ion is and draw the nucleophilic attack correct. Okay, the next question I had chosen was question 14. Deals with the Diels-Alder, deals with the Diels, right? There we go. So this is nothing more than a Diels-Alder reaction. This is something that we covered in this semester, Diels-Alder. And you can see that we have these two nitriles that are trans to each other. Right? This is a transalkene. And you can see that our diene is locked in the S-cis, right? Locked in S-cis. So this thing is ready to go. Right? It's ready to react. Now, since our diene is in a cyclic compound, we're going to end up with a bridged molecule. Right, if you want to draw the curved arrows for this mechanism, it's going to look something like this, where we have attack like this. We form a new carbon-carbon bond here, and then we put our double bond here. So we're going to end up with a bridged compound. We can eliminate both of these. Neither of these are bridged compounds. These are bridged compounds. I see a major problem with B, though. Huge problem. Because when you draw the product of this mechanism, right, you're going to have the one, 2, 3. So here we go. These are the 6 carbons of the ring. You're going to have a double bond here, okay? Then you're going to have the bond to the 2 carbons of your dienophile. And since the nitriles are trans, okay, one of them is going to be pointing down and one of them is going to be pointing up. Now that's my best drawing of what the product is, which would obviously be A. Because the major faux pas in B is that you're not going to end up with 2 double bonds in the molecule, right? You're only going to end up forming 1 double bond right there, right? This double bond, okay? So this one is pointing up, and this one is pointing down. So you don't even have to know the endo rule to solve this problem. Okay, so the answer to this one is A. Now you might be asking, like, hey, this looks like a wedge going the wrong way. This is a different way of drawing a dash, which I don't ever use. But this is actually supposed to be a dash. You can see how the ink there is a little bit weak. But yeah, anyhow. Let's move on to question number 16. Okay, so I'm going to ask you guys flat out, what's the answer to 16? Okay, we're taking, it says, which reagent, Y, so here's the reagent. So which reagent would be the best choice to complete this reaction? We're taking an alkene, and we're converting it to an epoxide. Can anybody help me out with that? Okay, Diego says C, right? Exactly. So everybody says C. Good. Okay, so when you recognize C, right, this is a peroxy acid. What are the 2 peroxy acids that we looked at? We looked at MCPBA, which is metachloroperbenzoic acid. So that's this guy. Okay, and then we looked at peroxyacetic acid, which is this guy. There we go, like that. So we looked at both of those. Those are used to do epoxidations. Okay, so we're making an epoxide. So this is an epoxidation. If you need to look that up, you know, what's the problems with the other one? Well, periodic acid, we never even looked at that in our class. If you look at these 2 here, these are both involved in dihydroxylation, aren't they? Right? These are both involved in syn dihydroxylation. So syn dihydroxylation. So neither of those are going to help us out, are they? All right. Osmium tetroxide or potassium permanganate. Anyhow, and periodic acid, again, it's not, I don't even think it's covered in our textbook. So we'll just eliminate that one. You can look it up if you want to, but I'm not going to ask you anything about periodic acid. Next question. Let's just switch gears. Let's go to a different section. So you got to bear with me here. Let me find it. Nucleophilic addition at carbonyl groups. So the first question I had chosen was number 4. Okay, let me get it stabilized here. Question number 4, just, you know, what's the expected product from this reaction? I'll give you a second to look at this one. If anybody's got an answer, just throw it at me, and I'm happy to take a look. Does anybody have any idea about this one? We're taking a ketone. All right, we're starting with a ketone, and we're treating it with this compound, which is called hydrazine. All right. And when we take a ketone and we treat it with hydrazine, we end up with a hydrazone. So a hydrazone. Could anybody identify which one of these is a hydrazone? Yeah, the answer is A. So this is, you know, I would say pretty pure memorization, you know, making a hydrazone from hydrazine and a ketone, but that's the reaction that we've looked at over the course of the semester. Here's another one, not this one, but number 6. Where is it? Number 6. This is a great question. This will show, I promise you, if you want to write the DAT or the MCAT or the whatever, future business leaders of America, I don't know. Any exam that involves organic chemistry is going to have some iteration of this question, number 6. Okay, very important in organic chemistry. It says, what's the main product that can be isolated from this reaction below? We're taking cyclohexanone. So we're starting with a ketone, and we're treating it with ethylene glycol. Ethylene glycol, right? Toluene sulfonic acid, so tosic acid, or as you guys call it, I don't know, I forget. What did we call it? PTSA? Toluene sulfonic acid. And C6H6, this just means you're doing the reaction in benzene. That's neither here nor there. The reason why you would do this reaction in benzene, now that I think of it, because benzene and water are immiscible. Okay, so this would be a good way to be able to remove water from a reaction using a Dean-Stark trap, which I went over with you. Okay, does anybody remember? Did anybody name the functional group that you would get? What that ketone would be converted to? Tosic acid, which is just a strong acid. So this is nothing more than a H plus PTSA. Did anybody name the functional group that we're going to make? Yes. Okay, so somebody says an acetal. Yep, you're right. So we're going to make an acetal. Right? What's an acetal? It's like having a carbon with two ethers attached, right? Kind of like that. And then your other groups, they could be hydrogens or they could be other carbons like that. Now, which one would be the correct acetal? Well, this is going to be after you form the first, after you form the hemiacetal, the acetal is going to be formed from the second hydroxyl, right? Because you get two hydroxyls here, and so you're going to end up with a cyclic acetal, and so the answer would be C. And this is just acetal formation. We even used an acetal as a protecting group in this class. Okay, let's move forward to question number 14. I'm going to give you a second to think about this one. Yeah, Sean, you're right. It's D, right? If we take the first one, it's methyl magnesium bromide, so that's our Grignard reagent. And if we attack here, right, and then protonate, that's going to give us the compound in the box. The next one, we're doing ethyl Grignard, and we're reacting with acetophenone. And yes, that's going to give us the same thing as well. The next one, we're using phenolithium as our nucleophile, okay, and we're using butanone. And if we do our nucleophilic attack here in protonation, so all of those will give us the correct product. I mean, you can see the major problem with D, right? I see a big problem here. Look, we have 1, 2, 3, 4 carbons coming off of the aromatic ring. Here we have 1, 2, 3, 4, 5. So you just have too many carbons. I mean, you could answer that, just by reading the question very carefully, right? If you were to get a nucleophilic attack like this, you'd have too many carbons, even though you still end up forming an alcohol. And so the answer is D. That one will not work. Let's move on to question 16. It says, what would be the product of this reaction? Well, I think the best thing we could do here would be to draw the mechanism. So this is, when we have this is called phenolithium, right? It's the same thing as drawing, a phenylcarbanion like that, which we know you can't have an sp2 hybridized carbanion like that unless it's stabilized by a metal like lithium. But anyhow, so we can treat that as if it's, a nucleophile like this. So we're going to get our nucleophilic attack like this. And then what are we going to end up? We're going to end up with something that looks like this. We'll have our oxygen like this, our phenyl. And then we're just going to protonate that with water, right? In the last step, it's just a proton transfer like that. And then we're going to end up with this compound. So nothing more than that. And if you look at the answers, the answer is B is the correct answer. So just a little practice with mechanisms, nothing more than that. And of course, you got to know, you got to be able to recognize a mechanism or two. Past organic chemistry. Question 17 deals with cuprates. Don't even think I put any questions in the exam about cuprates. There could be, don't quote me on that. But I don't remember putting one in. Anyhow, we have an alpha beta, right? This is called an alpha beta unsaturated ketone. And if we want to do a Michael addition to that, we would want to use a cuprate. So for this, we would use a cuprate. And so here's the cuprate right there. So that's something that we covered in class in detail. If you were to use a Grignard, for example, it would attack here. But since you have a cuprate, it's going to attack at the beta carbon like that. And then, of course, you could add something at the alpha, and we looked at that as well. Okay, let's move on to number 20. All right, all we're really trying to do today is just get some more review in. What is the product of this reaction sequence? We went over this in the practice quiz that I gave you. Just some classic, Wittig chemistry. So first, we're treating. So this is benzoyl chloride. This here is benzoyl chloride, and we're treating that with triphenylphosphine, right? C6H5. That's the same thing as a phenyl, and so this is PPH3, right? Which we know is a nucleophile. All right, we're going to do our nucleophilic attack like this. We'll lose the chloride. And then the intermediate that we would make would look like this, C6H5, CH2, and then it's going to be bound to the phosphorus with the 3 phenols like this. And then we're treating that with potassium T-butoxide, which is a strong base. And so what you're going to do then is you're going to remove this proton using potassium T-butoxide, right? And you're going to go from your phosphonium salt to your ylide, right, or your ylene. Doesn't matter. Okay, I'll draw the ylene. So then you would end up with this C6H5, 5, CH and P, PH3, like that. And then you're going to do a Wittig on this compound. And what's that? It's a C6H52CO. So that means you're going to do a Wittig with this guy. So you've got two phenols like that. Okay, so all you're going to end up doing is adding this piece, right, and replacing that oxygen with that. So it's definitely not this, and it's definitely not an alcohol. It's definitely not a ketone, right? You make an alkene from a Wittig, right? Now, to solve this problem, I mean, all you have to do is recognize that this is a Wittig reaction, right? And Wittig is a way to make an alkene. So if you had looked at the answers quickly and just said, well, this is the only one with an alkene, I'm done, like that. All right. There we go. Number 21. What's the product of this one? A little more Wittig chemistry for you here. So in the first step, we're treating a phosphonium salt with C4H9Li. That's the same thing as writing down butyllithium, which is just a really strong base. And so you have your, so you've got pH3, right? Remember, this is the same thing as pH. So you've got pH3, and then you got this, okay? Like that. You've only got one place where you have an acidic proton, and that's here. So I'll draw that proton out explicitly. Then your butyllithium is going to behave as a base, right? It's going to abstract that proton. So instead of having a phosphonium salt, you'll end up with your ylene. We'll draw the ylene. You'd also end up with butane plus lithium iodide. Those are neither here nor there right now. And then that's going to react with your ketone, right? That's going to react with the carbonyl. And what are you going to replace this oxygen with? You're going to replace it with this portion, is all. So if we look at all of these possible answers, you know, the compound should have a double bond in it. So we get double bonds, you know. There's no alkene in here. So we can eliminate B. And then it's not going to be an alcohol, is it, right? So we can eliminate those, right? All you're doing is replacing this oxygen with a CH2 in the Wittig reaction, and that's what's being done right here. That's the CH2 that replaces the oxygen. And so the correct answer is A, like that. And if you need some practice drawing out the mechanism, right, so I'll have to draw just the bond line structure here. So we have 1, 2, 3, like this, okay? So remember, we form the oxetane like that, right? And then it undergoes fragmentation to give you the final product. So make sure you look over your Wittig chemistry. Right? Wittig is a very important reaction. Wittig won a Nobel Prize. You did some Wittig chemistry in the lab if you took chemistry 3112, which most of you did. Okay, let's move on to question. So now we're in nucleophilic substitutions at a carbonyl group. Here we go. Oh, here we go. So nucleophilic acyl substitution, I mean, is covered in this question, question 3. And this is something that we went over in excruciating detail in the carboxylic acids and their derivatives chapter, which is chapter 20. So this question comes straight out of chapter 20. We even had there's even a table in our textbook, and I put it in the slides that discuss the reactivity of amides, esters, acid anhydrides, and acid chlorides, right? Here we have an amide. Here we have an ester. Here we have an anhydride. And here we have an acid chloride. And it's just reacting, you know, which one of these is going to react most slowly with sodium hydroxide? Well, we went over these, you know, as terms of which one is going to react the fastest. And the fastest, most reactive one is going to be, right, the acid. Fastest, okay, it's going to be the acid chloride. Right? Does anybody remember which one of these would be the least reactive, the slowest? Yeah, exactly. So the answer is the amide is going to react the slowest, right? If you go, they're actually in order, going from slowest to fastest. Okay. So again, this is covered in chapter 20 if you need to review this. But if you think about, what's the leaving group? Here I have a chloride, here I have an acetate, here I have a methoxide, and here I have a methyl amide. Well, the best leaving group is going to be the conjugate base of the strongest acid, right? Which would be, here it would be HCl, here it'd be acetic acid, here it'd be methanol, and here it would be methylamine. So you can think about it in that way. Okay, let's go over here to number 6. It says here, which reagent is benzoic acid readily converted to benzoyl chloride in a high yield? Again, I'd say this one's pretty much a memorization. The mechanism is covered in our textbook. So this is a reaction that we used many times in the carboxylic acid chapter. And in the amines chapter, we looked at it too. Does anybody have an idea about this one? It's not HCl. What would be the best set of conditions? Okay, so if I want to convert a carboxylic acid to an acid chloride, my best choice is to use SOCl2, which is called thionyl chloride. Right, thionyl chloride. Okay, let's move on from there. Number 8. What product would you expect to isolate from these reactants? So we're taking an acid chloride and we're treating it with an amine. And this is something that we went over, and in our book, he always says excess. He always makes a point of saying excess. It's neither here nor there, really. I mean, either way. But, an amine is a good nucleophile, isn't it? And acetyl chloride is going to be an extremely powerful electrophile. All right, so we're going to get a nucleophilic attack like this, followed by loss of a leaving group, and then deprotonation, or loss of the chloride followed by deprotonation with the second equivalent of the amine. And who could tell me what would be the answer here, the most reasonable answer? And this is covered in chapter 20. One of the biggest chapters we looked at. Anybody have an idea? Right, then the second equivalent of the base is going to come along and remove that proton, right? And then it's going to give us D plus. We're going to end up with ethyl ammonium chloride. Okay, so the answer is D. We end up making an amide in this case. Okay, again, this is chapter 20. If you need to review your chapter 20 material, we look at a lot of reactions in chapter 20. Okay, let's move on to another one. Number 10. So basic hydrolysis of an amide. What are the products of this reaction? Well, if we're hydrolyzing an amide, right, we're going to end up breaking which bond? Well, if we draw the bond line structure of this amide, okay, so this is N-ethyl acetamide, okay, the hydroxide is a powerful nucleophile, very powerful, and so it's going to attack, this carbon here, right, to form a tetrahedral intermediate. So what's the net result? Is we're going to end up breaking this bond. Now, that means we're going to end up producing the acetate ion, right, which is only shown here, right? Since we're in base, we're not going to end up with acetic acid. We're going to end up with acetate, and then you're also going to end up with ethylamine, okay, the basic hydrolysis of an amide. So if you need to review that, basic hydrolysis of and amide. Okay, number 13. Which reaction sequence is preferred for this conversion? I'll give you a second to take a gander at it. This is a reaction that you would have had to have memorized. It was covered in chapter 21. So the alpha carbon chemistry. So it's not in chapter 20. This is a chapter 21 reaction. Okay, and we kind of looked at it pretty quickly, but a way to convert a carboxylic acid to a methyl ketone is to first treat it with vinyl chloride. That gives you the acid chloride like this. And then in the second step, we treat that with a methyl cuprate. So we treat it with methyl cuprate like that. So if you want to review that reaction, there it is. Next one, number 14, is what is the product of this Grignard reaction? Well, this is a Grignard reaction on a cyclic ester, right? Do you guys remember what it's called when we have a cyclic ester? Got a special fancy name. Yeah, it's called a lactone. Absolutely. Oh, there we go, a lactone. Well, I think the best thing that we could do here would be to maybe draw the mechanism. But you should remember that when you take an ester and you treat it with a Grignard, that Grignards add 2 times to esters. Okay, we get a double addition. You're like, what do you mean by that? Well, let's see here. Let's start by drawing the lactone. And here's our lactone. It looks something like that. Fix that up a little bit. There we go. Okay, well, in the first step, we're going to take our ethyl Grignard. I'll kind of draw it a little simpler here. Excuse me. We're going to get a nucleophilic attack like this, and that's going to result in a tetrahedral intermediate, which will look like this. Excuse me. Then we're going to open up the ring by the tetrahedral intermediate like this. Here's where you want to count your carbons very carefully. We have 1, 2, 3, 4, 5, 6 carbons total. I'm going to have my ethyl group. Maybe I'll draw it explicitly. Why don't we draw a carbonyl, then we have an ethyl group. So we have 1, 2, 3, 4. So 1, 2, 3, 4. And then we have our oxygen like this. Yep. 1, 2, 3, 4. Just making sure I got to count it all right. Okay. Now, what's going to happen is a second equivalent of the ethyl magnesium bromide can react with the ketone that's formed like this. Then we end up with this interesting compound. So we end up with a tertiary alcohol in the end, right, on one side. So we have our ethyl group here. We have another ethyl group. Then we have 1, 2, 3, 4, right? And then both of those end up getting protonated by H2O and H plus. And then we end up with this compound. So we've got a tertiary alcohol here. Oops, nope, I didn't mean to do that. There we go. And 1, 2, 3, 4. And there we have it. So that's the compound you would make, right? Because a Grignard adds twice. Grignard adds twice to an ester. Okay, so let's go back. And let's find that problem. It's problem 14. Must be getting close. There we go. So the green yard added twice. So, I mean, immediately you can scratch off, cross out the first two, right? Because they have a ring in them. That's not even anywhere near correct. And you wouldn't have a double bond to an oxygen either. You wouldn't have any carbonyl left. And so the answer is this one right here. It's going to be D. Next one I picked was number 15, which is just another straight ahead, you know, your bread and butter sort of synthesis problem. It says, which reaction sequence would best accomplish this transformation? We want to take this carboxylic acid and treat it to, and convert it rather to a tertiary amide. Well, if you look at the first one, second one, sorry, it's treatment with ammonia. I mean, that's not going to do anything. The next one is a reduction. That sodium borohydride isn't even going to reduce a carboxylic acid. And if we use dimethyl amide, that's just a strong base. That's just going to do a deprotonation. But we know that in A, if you treat this with SOCl2, right, thionyl chloride, it's come up quite a bit this morning, you're going to end up producing the acid chloride, which is a really powerful, super powerful, mega powerful electrophile. And then your base, right, your base, the dimethylamine, is going to come in, it's going to react. And we already looked at that mechanism this morning, right? So there's a few steps there that I'm leaving out. But anyhow, so there we have it. Let's see here. Number 16. What's the product of this reduction? Ooh, this is one that you just kind of have to memorize. Okay, this is the reduction of amides. So reduction of amides. The mechanism for this reaction is not covered in our textbook at all. It's left out completely. I have a note here that I wrote down, and this is, yeah, just reduction of amides is where it's found. Anyhow, so again, nothing more than a memorization question. And what happens when you treat an amide with lithium aluminum hydride is that you just end up removing the carbonyl, right, and adding hydrogens there. So it's just reduction of the carbonyl, nothing more than that. And so you end up with D like that. Good.